Hi guys, I'll explain you the advantages and disadvantages of using big decision trees and D trees and different ID3 or CART or C4.5 algorithms for prediction purpose in machine learning. So you can see advantages. Light is falling on this and you can't see. So in advantages, I have actually drawn a particular tree over here, and the tree is actually vertical here. So this is the grandparent node, B and C are the parent nodes, and D, E, F are the child nodes. Okay, so suppose if here you can see there is no child, only one child is there for one of the parent. So there is no second child here, so the tree is not complete here, but still the algorithm works properly, and the prediction and all the information gain calculations, entropy calculations, they work excellently fine. So the advantage here is the decision tree, it works very well with missing values. So you don't, like, usually while doing EDA or exploratory data analysis, then when we have missing values, we replace it with a mean value, median value, or we encode the values, categorical values. So when you have the ID3 or C4.5, then if you have the missing values, then there is a you don't have to actually encode it. So it actually works well even when you have outliers. That is a lot of when you actually plot a box plot, then you can see box plot actually looks like this, like this. So suppose if my data is like this, okay, as you can see here, 0, 0.25, 0.5, 0.75, 0.1. So this is my box plot. So most of my data is present between the second quartile range, that is 0.25 and between 0.5. And here I have written lots of bugs and like some kind of circles, though these are outliers over here. So outliers are something where there is missing values or repetitive values or redundant values or continuous values, which are actually not important, because if most of the data is like outlier data, then the decision might be biased over here. So you know that entropy, if there is lots of suppose if this branch, it has parent one is B and child also it is B only, then because then usually decision tree won't be traveling over here to see if the child is not D but it was B here, then the entropy over here would be 0 for this particular node, so it will actually not even consider to go over there. So the entropy would be 0 over there, and since the machine learning algorithm will not learn anything new if instead of D, B is there over here, and it will not throw any errors, but the algorithm works well, and you will get a biased output because the branches will actually not be visited at all in decision trees if you have same node values or if you have continuous data. So that is you can say it actually works fast when you have small data sets, and like suppose if I have my complete data set as A's and there is only one B, then obviously decision tree will say the most of the data is A and there is only one B, so the probability for A will be information gain for A would be higher than it would be higher than B, since there is only one B, but since it has already checked entropy for A, which will be 0, but entropy for B would be some 1, or some -1 divided by B's plus total number of A's in the data set. So you see, like that it works very well for small data sets, but when you have very big data sets, okay, we are going on the disadvantages side now. When we have the big data sets, then some trees over here, like instead of D if there is B, or like more number of missing values are there on this side, like outliers are there, then those particular data set will be cut, and that branches will be cut, and this concept is called as pruning. And Actually this whenever it is cutting a lot, then underfitting happens, or if it keeps traveling this side a lot, and because there are more and more features or granular features and different features, and it learns more about this particular side. And since it is very biased and it keeps traveling, then it might give you a bigger output here. So the computational cost, and like suppose if I'm using Azure cloud space or AWS cloud space, and if I want to run this particular secant algorithm or 4.5 or ID3 on AWS or Azure, then my computation cost will be actually very high, because that for every new training data, like whenever I get clickstream data or finance banking data, then I keep introducing more and more training data, and every time how many ever branches are there or nodes are there, it keeps traveling and traveling and traveling again and again, and it gives you sometimes biased output. So you introduce new data so that bias or variance is not there so much. If you have a lot of variety in the data set, then the bias actually reduces and you get a equal balanced output. So the computational cost is actually high if you want to increase the accurate predictions for decision trees and sensitization. The disadvantage here is, suppose if I have information gain for a comma b to be somewhere between 0.2, and I have information gain for a comma c to be 0.38, say for example. But I thought instead of why should I have a child e? Instead of the child e, I will cut it off and I will have child f here. And because the parent thought that he'll give it off, because we have cut it year and year, then the automatically over here information gain will reduce and it will become 0.15. Because you see, if we have redundant data, or if even one change or small attribute changes or labeling changes happen, then the complete result of the information gain entropy for all the trees has to be calculated again. So whatever trees or branches or child nodes were there below over here on this side, they have to be calculated again. Here we have a smaller tree, but usually the depth of the trees might be like 23 million, or based on the big data set, whenever we have training data will be added, the size will actually increase. So every time it has to be calculated for all the nodes. So that's the reason it is a very sensitive algorithm. And even if small variety of changes will be done, then we have to actually train the algorithm to recognize the data, and so that the algorithm performance improves. Then we can actually do hyperparameter tuning, or introduce different kinds of decision trees, or even control the depth of the tree. We don't want to build a tree which is having height of 23 million, but we want to build a tree which has 15 million height. So we can control the height of the data set, and the width of the data set, the number of leaves or the number of children, and also the pruning capacity, and to also reduce the overfitting. There are scikit-learn parameters that can control underfitting and overfitting, and also we can introduce a variety of the data set, the split condition. Like every time you see it is being split, then you can control how many times splits can be conditioned. And if I want to see, if I have redundant data, if I want to have only one data, and redundant data like FFFFF should not be there, only one f or child should be there, so that we want to reduce the cost or optimization cost. Then we can actually also introduce a particular parameter which is called as split criteria or cross validation. So for cross validation, every time whenever we are splitting our data set, some of the data set is left for training, testing and validation in machine learning. So like we will see based upon the cross validation, like and k-fold validation, like that is our decision tree split criteria working well, and what would be the optimization cost. Like sometimes where the biggest problem in big data pruning and overfitting is underfitting is for every minute or for number of hours we keep our notebooks running in the Azure Databricks. In those many hours, our company has to pay Azure clients or AWS clients. So that's the reason when you think of applying decision tree algorithms, then you have to actually evaluate the cost capacity before just applying a cart algorithm directly. So in most cases in financial banking it will work, but if you have health data sets, or like sometimes a critical financial automation recommendation data sets, and that kind of data sets, if you want to make small changes also, then the cost capacity and the error mistakes will actually be very big. So before doing that, we have to actually test our algorithms using cross validation or stratification, like that. And that is very important. So that one particular problem is there. So it works actually very well for small data sets. How do I know if a data set is small and it is not a big data set? You say a small data set when your data is not live streaming, when your data volume is actually static or it is stagnant, or if you are working on sample data sets, like if you have big data like Hadoop data sets, and if you are taking a sample from your Hadoop blob, then you can say it is a small data set. And if you will apply this algorithm on your Hadoop data set, then you should not use a big data set, but you should use LGBM or automated machine learning light gradient boosting models, or light random forest models, or cat boosting models. So you should use a forest kind of algorithm over there. So when and a small data set is somewhere where your variety of the data is also not there. Or if you have a data set variety, like if you are having data of JSON type, blob type, ETL data, and XML data, like this, you have different kinds of data bulk which is there, and it is stored in the same database. Then and if it keeps getting added and added and added from Jira or from ETL tools, then usually it is not a small data set, it's a big data set. So Oracle database, or else a SQL database, or IBM Bluemix database, it is a small data set. And if you actually transformed your data, or if you join your data set for performing it using Airflow, or for small data automation, for web recommendation, for analytics, like that, it is small data set. Okay, because you are actually not pumping your data daily or on hourly basis, like you do not add 4 GB or 18 GB or data every hour, like that. So it is a small data set. So that was about the advantages, applications, and what else did I explain? Yeah, statistical metrics in decision tree and different types of decision tree. What is a decision tree? So I've explained all this, and I also coded decision tree. Like I have coded the regression I have done. I've utilized the decision tree regression model on bike rental estimation, and also demand estimation, like daily rental demand estimation. I have also participated in another Kaggle competitions using decision tree. I'll try to find those notebooks where I have utilized decision tree classification as well. You can find those links below. I will attach it below in the description box. And if you like my video, and if you want to learn about any new algorithm where I can apply the numerical example like cat boosting or LGBM, you won't find numerical problems or statistical metrics explained very deeply. Usually they are present in research papers, so I can try to explain it using numeric problems, because that will be revision for me, as well as I'll be able to demonstrate the algorithm for you using numbers or statistical problems, so you'll be able to remember where and where not to apply this particular algorithm. So if you like my video and if you want to see more videos like this, and if you want to try out Azure or GCP datasets and how practical application, then please subscribe to my channel, and also click the bell icon so that you get regular notifications from my videos, and also like my video. Ta-ta! See you soon!